Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and today we're going to continue our discussion in variable coefficients, second order ordinary differential equations. And last class we talked about that a semi-general approach to these type of equations would be to expand in a power series and use this power series approach to determine some kind of recurrence relation that would allow us to get to the coefficients, to learn how the coefficients behave, and therefore formulating the final result, the final solution of the equation in terms of these power series with known coefficients at the end of the day. Now, we learned also that this power series approach is limited in a sense because this is a Taylor series, and Taylor series have what's called a radius of convergency. So if the functions or the coefficients in the differential equations happen to be singular, you cannot set the point of expansion of this Taylor series very close to the singularities, because then the series diverges and the solution is not valid. So you have to get away from the singularity or hope that these functions don't have singularities at all, which commonly they do. Now, it turns out that there's a way by which you can modify this approach so that you can expand these power series about, or set the point of expansion about a singularity of these functions, as long as the singularities on the function satisfy certain properties. And this is called the Frobenious method, which I am going to explain today, which is going to lead to the solution of very common and famous equations that are going to be very much used for us in the coming weeks. So this is modeling methods in ME, and we are going to talk about the Frobenious method. So if you are given a second order ODE, and it's written in the generalized form with P and Q, where P and Q are these variable coefficients, and it turns out that they may be singular. Now, we saw that, for example, in the Legendre's equation, which was the last equation that we attempted to solve last class, these functions were singular in the Legendre's equation, but they were singular about points x equal 1 and x equal -1. So we managed to expand the Taylor series, or the power series, about point 0, having a radius of convergency of the entire diameter, or the entire radius of the singularity. So the radius of convergency was the entire span of the singularity of the functions, which actually happens to work out for that particular problem. But in some cases, it will not, because the singularity is right at 0, or right at a point where you need to expand. So let's assume that P and Q are singular functions. Now, the point x0 is called, and we're going to say they're singular at x equal x0. Right? So the point x0 is called a regular singular point if, so as long as these conditions apply, if you take the limit as x goes to x0 of x minus x0 times p of x, and you get a finite number, so the singularity is eliminated. So if you multiply p of x by a first order polynomial, x minus x0, and then the singularity is removed, and if you take the limit when x goes to x0 of x minus x0 squared times q of x, and it's also finite. So if one of these happens to be singular, right, and then you multiply the first one by a first order polynomial and the second one by a second order polynomial, and then you remove that singularity, then this is known as a regular singular point. Notice that not both of them need to be singular, as long as one of them is singular and you can actually remove the singularity that way, then it works. Now, for example, if one of these is not singular, like for example, let's say q is not a singular function, If it's not a singular function and you multiply it by a second order polynomial, it's still not a singular function. You're going to get a finite result for the limit. So it still works. Then we can try a solution in terms of what's called a Frobenious expansion as, so we're going to say the same thing. We're going to expand from n equals 0 to infinity. It's going to be a power series with infinite number of coefficients. We're going to call them an now. We're going to expand about this point of expansion x0, which is the singularity. So notice that we are expanding about the singularity, but instead of these being to the power of n, it's going to be to the power of n plus k. All right. Now, for now, let x0 be equal to 0 for simplicity, right? So let's assume that this particular function has singularity at 0. And then if y of x then is equal to, I'm going to write it here, y of x is then equal to the summation from n equals 0 to infinity an x to the n plus k. And therefore, dy dx, the derivative of these with respect to x is the summation from n equals 0 to infinity of an n plus k x to the n plus k minus 1, and the second derivative of these power series is the summation from n equals 0 to infinity an n plus k minus 1 x to the n plus k minus 2. All right, so notice that when we do this differentiation, the starting point of the series doesn't change to 1 and to 2 because we don't know what k is. K can be a fractional power, it can be 0.5, so therefore, well, when you take the derivative of x to the 1/2, for example, at n equals 0, you get x to the minus 1/2, so the minus sign still applies. So the minus exponent here would still apply. All right, so let's keep formulating this. So if this is the case, you can plug this back into ODE. So you get summation from n equals 0 to infinity. We're going to take these three series and plug them into the ODE. an n plus k minus 1 x to the m plus k minus 2 plus p of x times the summation from n equals 0 to infinity of an n plus k x to the n plus k minus 1 plus q of x times the summation from n equals 0 to infinity an x to the n plus k is equal to 0. Okay, so that's that assumption, that trial function, that power series, now plugged into the ODE. Now recall that x0 equals 0 is a regular singularity. Therefore, we may assume, so remember that the reason why we did all this is because these functions px and qx satisfy this condition of regular singularity. So if that's the case, then I can say that p of x is equal to some coefficient p minus 1 divided by x plus p0 plus p1x plus p2x squared plus so on and so forth. So technically I can take that function px and expand it into its own Taylor series. So px is a known function, it's very simple to evaluate. And since it's a regular singularity, that means that if I did multiply this by an x, then the singularity will be gone. Then I can assume that this function can be expanded as a Taylor series plus this singular term right here, where p minus 1, p0, p1 are just these coefficients of the Taylor expansion. And qx, same thing, but qx is a singularity that is removed by a second order polynomial, so I can just say that this goes like this, plus q0 plus q1x plus q2x squared plus so on and so forth, right? So one is a function that has a singularity, a single order singularity, and the other one is a function that has a second order singularity, and therefore we can expand those functions that way. So I'm going to take these, plug them back into the differential equation, and that is going to result into the following. So the first series goes like an n plus k minus 1 times x to the n plus k minus 2 plus pk, which is p minus 1 divided by x, plus p0 plus p1 times x, plus so on and so forth, multiplying the summation from n equals 0 to infinity of an times n plus k times x to the n plus k minus 1. And the last one would be q minus 2 x squared plus q minus 1 x plus q0 plus q1x plus so on and so forth. So that power series also for the function q, n equals 0 to infinity, an x to the n plus k, and all of these is equal to 0. Right? So then I can rearrange these, and I can very easily show that this would look like this. So I'm going to try to squeeze this into these three lines. This will be a0. So now I'm expanding this series here. Times k, when n is equal to 0, then it goes like this. K times k minus 1 plus a0 times k p minus 1 plus a0 times q minus 2 times x to the k minus 2. So I'm looking for the common factors between these three series. This one at n equals 0, this one at n equals 0. Okay, so when n is equal to 0, I get x to the n plus k to the k minus 1, and then when I get x to the k minus 1 and I multiply times this term, I get x to the n to the k minus 2, multiplying times p minus 1, and the same thing here. So that's k minus 2 plus I get a1 times k plus 1 times k plus so on and so forth, x to the k minus 1 plus, so the point I'm trying to make is I can expand every single element of this series and group them together, and I can take one element from each of the series and group them together, and I can keep on going, and at the end this is all equal to 0. So there's a summation. So basically what I can deduce from this is that there's an initial equation, therefore the initial equation for k is, so I can take these, either this is equal to 0 or this is equal to 0, but this, since this cannot be equal to 0, so I'm going to just basically compare orders between the left and the right. So anything that multiply k minus 2, x to the k minus 2 on the left has to be equal to anything that multiply x to the k minus 2 on the right. So therefore this coefficient has to be equal to 0. So I can take the a0 out as a common factor, and that would be k times k minus 1 plus k p minus 1 plus q minus 2 is equal to 0. And this right here is a quadratic function for k. And basically, once you have k, then you can plug it back into the solution that says that y is the summation of an, x, n plus k. So you find basically by doing this, you can very easily find what k needs to be for the series solution to work. All right, so there are certain rules. Then notice that this is a quadratic equation. This is a k squared times something that multiplies k times something that's a common factor. So you can use the quadratic equation to find k. So those k's can be real, complex, repeated, so on and so forth. So there's a set of rules here. So rules for k. 1. If k1 is different than k2, and k1 minus k2 are not different, the difference between k1 and k2 is not an integer, so they're not separated by an integer, then basically the solution y is equal to c1 y1x plus c2 y2x, such that y1x is equal to the summation from n equals 0 to infinity of an times x to the n plus k1. Remember, in all of these, we're assuming that the point of expansion is 0, so it's not x minus x0, it's just x minus 0. And y2 of x is equal to the summation from n equals 0 to infinity of an x to the n plus k2. So there's the two roots, and it works out that way. If k1 is different than k2 and k1 minus k2 is an integer, then again the solution y of x is equal to c1 times y1 of x plus c2 times y2 of x, such that y1 of x is equal to the summation from n equals 0 to infinity of an x to the n plus k1, and y2 of x is equal to the summation from n equals 0 to infinity of a y1 of x times the log of x plus the summation. Actually, this summation sign doesn't go here, so let's erase it. So it's just a times y1 times the log of x times the summation from n equals 0 to infinity of dn x to the power of n plus k2. So it's just an algebraic mix of k1 and k2. And finally, 3, if k1 is equal to k2, which is equal to some k, then again y of x is equal to c1 y1 of x plus c2 y2 of x, where y1 of x is equal to the summation from n equals 0 to infinity of an x to the power of n plus k, and y2 of x is equal to x times the summation from n equals 0 to infinity dn x to the power of n plus k plus a y1 of x times the log of x. So it's slightly different from the previous one. So this is how it goes. You have the three options, and by the way, notice that we're always assuming in this case that this solution k1 and k2 are real. But if this were to be imaginary, there's a little transformation that I'll show you in the next class that that works just fine. All right, so let's go straight to an example to see how this works. In fact, I think I'm going to leave all the examples for the next lecture. So I just wanted to introduce the Frobenious method as a way to approximate this type of solutions. So that's it. Let's just do it until here. This is the analytical formulation of the Frobenious method. I'm going to leave the examples to next class. So thank you for your attention, and I'll see you next lecture.